All right, so thank you. If you've joined us now, you are here at one of iGuide's virtual consulting offices, VCOs. These are weekly presentations that we offer on, excuse me, on technical topics. My name's Diana Sinton. I'm a project manager for iGuide. And this is a regular Zoom meeting, so we request that you keep your own microphones muted unless you're presenting. It is being recorded, as you know, and once the file is processed, we'll have it up on our website to share more broadly. Um, let's see, it's 3 after the hour. I'm going to wait for another 30 seconds or so before I turn it over to
I've
the
just
audience.
texted Brandon just in case.
Okay, there is, if you've got a question that comes up during the presentation, please feel free to type it into the chat, but I'm going to request, usually it works better to have the presenters address questions at the end of the talk instead of throughout, but I'll leave that up to them as well. And we'll yeah, let's go ahead and get started. We see a couple more people joining. People will continue to join, but I'm going to turn it over to
To Lance.
Lance, who's going to be the first presenter, and it looks like we've got things all set. So Lance, it's all yours. Take it away.
Thank you very much. Thanks, Diana, for hosting all of this. Thanks to NSF iGuide for making all of this possible. And basically, as I'm getting my Zoom etiquette nice and organized, yeah. So basically, we are really grateful to be with you today. I'm gonna set a timer. So basically, our plan is to go for about 30 minutes. We've got three of us that are going to be presenting. I'm here with Huang and Brandon Voelker, PhD students, who really I had the privilege and pleasure to lead as a team leader for the DeepEarth project for a summer school program that we all got together in Boulder, Colorado for a week. This was a very, very fun time. And I'm just happy just to comment personally for a second and say, we were basically really trying to understand how we can build this state-of-the-art AI model for understanding ecological properties. And in our case, we were very focused on understanding fire. So I put a little fire emoji on the planet there. And and basically we were sort of combining lots of data analysis, which we'll get into, and modeling and so forth. And there were five of us, five PhD students plus me. And we sort of combined this analysis with actually going into the field. This just strikes me as being meaningful that we actually went to sort of the wildland urban interface in Boulder, Colorado, where there's drought and fire risk regions. And we picked up some of these plants, and I was like, guys, this is live fuel moisture content. Like you can see how there's no water in the plant. Like, do you think this will burn? And everyone's like, yes. So these kinds of moments are very special, and you don't get them, without bringing everyone together. And I think all of us are very grateful for this. So just saying thanks and rehashing that moment. I do want to kind of broadly introduce the Deep Earth project. So just to say one quick thing, this is the whole Deep Earth model. For those who are not familiar, I think probably at least half of us will be familiar with this model at this point. Basically, the model is anywhere on the planet and any time, we should have a deep vector representation, which you can project potentially any number of data modalities into. And you should be able to build this self-supervised deep learning model that allows you to make predictions. So it's basically any kind of physical system can be measured across many modalities. And then the our model is one that will learn continuous distributions across space and time. And so this XYZT coordinate, this is the name of the game for this model is XYZT. That is actually the University of Illinois Urbana-Champaign, where we give credit to sort of the iGuide program. And anyways, I'm just basically wanted to say that I was thinking about putting something fancy with like a Gaussian distribution in here because this is a global talk. but I just sort of thought I'd keep it simple. So, all right, so I'm going to move on. Most of the meat you're going to get from Chin and Brandon, but I am going to present some cool things. So, I'm going to continue with the sort of politics for a moment and basically say thanks to a lot of people and institutions. So, first and foremost, thanks to iGuide, Institute for Geospatial Understanding through an Integrated Discovery Environment. Really, our work that we're doing today has been critically seeded and advanced. So the sprouts have been grown, and we're actually seeing some of these shrubs and trees growing because of iGuide. So thank you. Um, and there was also folks from the beginning across the University of Florida and Stanford University. We have one attending right now, Daniel Niamati, um, who've been sort of critical in conceiving of the models that we're presenting today. So I really want to give credit to them and also developing them and supporting them as we've gone further. Uh, Brandon is from the University of Houston, and Cheen is from the Arizona State University. And then some of these large tech companies have been supportive, folks who work there or have worked there. And basically, the Allen Institute for AI, we just we have an hour-long presentation. So if you like hearing me talk for an hour, you can watch a much more thorough introduction to DeepEarth. So I want to say that because I'm not going to cover all the details, basically. Um, and we are going to focus on fire ecology quite a bit, as well as some properties that Chin has been working on with Earth4D. And yeah, I just want to say that this model is designed to sort of address and solve a gap in ecological modeling because we recognize that there's a lot of work, for example, in climate foundation models or foundation models for, let's say, various fields of biology and so forth. But really, the field of ecology, at the point where you can predict what's happening across a landscape and all these physical systems coming together, we feel is underserved. And so we're really happy to focus DeepEarth on that. And so we work with landscape architecture organizations, and ecodash is the company that I'm coming from, basically. So all of this comes back to, can we simulate the ecosystem? This is the high level idea. So basically, can you get to a point where you look outside and we have the equivalent of what you might think of as a sort of digital twin of every plant, every flower, every hummingbird flying through. And the digital twin is one that is basically representing not just the spatial distribution at a very high precision, just as if it was a 3D model, but one that basically, truly could begin to animate the probability distributions of the hummingbird flying from flower to flower. And so that's where we're at today. I think basically, I can tell you with certainty that's where we're going, and I can tell you that the type of work that Chin and Brendan will, elaborate on, and then I'll, share a bit more insight on. We really are at the stage where we're basically thinking about taking these big global geospatial models, the geo AI models that iGuide has supported so much, and basically really being able to model at the landscape scale with these models, things like what is the fire risk of that individual plant species, in its current immature state or its current overgrown, dry, drubby leaf, dry leaf state, right next to the house. Is that a fire risk for the house? And I'm saying it very particularly like that because these are decisions that professionals in the field actually need to make. So our goal has always been to sort of bridge that gap between the sciences and academia, and also basically, with professionals in the field. So this is where I spend plenty of time on because I think it's what matters. It's what's actually going to drive the impact in all of our work. So I'm happy to remind us. Um, I did want to say one more nice thing because I think this is about a fire ecology. I'm intentionally putting something in here. It's not about fire ecology, but it is where the model originally came from. And basically, DeepEarth was originally designed, and one of my personal passions is ultimately to make sure that DeepEarth does predict the flowering of plants and the pollinators that visit the plants. And I'm mentioning this because it turns out that, as I'll get to shortly, when you're designing these, when you're basically modeling these landscapes and you're modeling these environments with models like DeepEarth, you have the opportunity, perhaps for the first time in history, to basically capture so many different data sources and to take your AI model and to pursue what you would describe as a multi-objective optimization, where you really can pursue, let's say, modeling of reduced fire risk, as well as modeling of pollinator-friendly planting designs. And I'm saying this because, fire ecology is one thing that we're going to solve. Pollinator, distributions to support the local wildlife is another thing that we're going to solve. And the ability to create a flourishing garden across all seasons is another thing. And there's literally deep earth models in development across all three of those things right now. So I'm saying that because you can expect all of this to eventually come together in a digital twin where folks in the professional fields of landscape architecture, environmental management, and so forth are literally using these tools that we're presenting today to simulate these ecosystems and to solve several problems at the same time. Happy to say that. To bring us to fire real quick, basically, you know, so what we're looking at right now is a before and after color-coded LiDAR topography in the Palisades area for Los Angeles in early 2025. And basically what we just see, just to summarize this real quick, is a lot more red, which -5 meters. We destroyed a lot of things during those fires. I mean, it's what happened. And I just want to basically bring the gravity of what we're doing here to bear for everyone and say, this is a real house that was burned down. That tree didn't burn down, but the house did. And my sort of just reminder here is that the work that we're doing influences policies that ultimately, maybe impacts whether a house like this gets burned down or not. And this is just reds are all the houses that have been burned down. I just wanted to kind of, give us that visual and reminder of what we're doing and why we're doing all of the deep models that you're going to hear shortly. So I'm not going to have time actually as I look at my timer, but to go into detail, but I did promise you can learn more about these concepts of self-supervised learning, which is the idea that basically you can sort of take any data set and take a AI model to learn to regenerate that data set. That's a core principle of DeepEarth. Another core principle is that it's multimodal, which means that you basically can take several different channels like satellite imagery and iNaturalist imagery and ultimately learn to reconstruct that simultaneously such that information from one modality is used to infer information from other modalities. We think this is a key concept to ultimately solve the very complicated ecological modeling problems we're addressing. We do have models for the multimodal autoencoding that we're very excited to use that we've been getting early stage prototyping results on. And the DeepEarth model as a whole is quite clear to us in terms of all the different components. But what I want to do is basically, before I hand off to Chin, just say that we are basically working with professionals on these types of models. And we are solving, this is a fire safe, fire smart landscape design that's also friendly for pollinators. But I want to hand it off to Chin and not take any more of their time and basically say one thing about Chin. Like I remember handing Chin the problem to pursue, the Earth 4D, thinking, boy, this is a really tough thing. I don't think this is the riskiest and hardest project of the 5 PhD students. And I think Chin emerged as sort of, let's just say that I'm very, very impressed by her work. And basically, the results that she got were by far the most spectacular, frankly. So I'm very excited to introduce Chin and say thanks to everyone for being with us today. So Chin, you can take it away. I'll go ahead and stop sharing my screen because I think it'll be best if we just switch and she can control her own slides, basically. So I'll stop sharing.
Okay, thank you so much for your nice words, Lance. Okay, so I will share my screen. Okay, so yeah, hi everyone. My name is Chin. So to start with, let's look at the core idea that inspired everything, the multi-resolution hash encoder, originally from NVIDIA's work in 2022. So let's explain it in simple terms. There was a way to make a small neural network learn extremely fine 3D details, for example, reconstructing realistic scenes from photographs in just a second instead of hours. And here's how it works. Imagine several overlapping 3D grids. Coarse ones capture big structure, while the fine ones capture details. Each grid corner stores a tiny learned vector, a numerical fingerprint of what's there. So when you input a coordinate, the system looks up nearby neighbors, the corners, interpolates their vectors, and feeds that into a neural network. This multi-scale design allows the model represent both global and local patterns efficiently. It is super fast, parallelizable, and scales beautifully on GPUs, thanks to CUDA. And that's the building block we later extend from 3D space to 4D space-time, which becomes the Earth 4D. And yeah, the next big step comes from a model called Grid 4D, where I study a lot during the summer school. And the Grid 4D applied the same idea to dynamic scenes, basically 3D space evolving over time. Grid 4D introduced 4D decomposed hash encoding. Instead of one 4D grid, it splits the data into several lower dimensional grids, one being purely spatial grid, XYZ, and the other three spatial temporal projections as XYT, YZT, XZT, as you can see in their illustration here. And each grid captures different relationship between space and time. Features from those grids go through spatial and temporal NLPs and an attention module that learns how objects move or change. So building on that, we adapted and created Earth 4D. Same principle, but now for a bigger scale, planetary scale data. The goal is to encode how Earth's systems evolve through both space and time, not just pixels in a video, but more on environmental processes themselves. And yeah, let's look at the idea of Earth 4D. So that's how it works conceptually. So we can start from real coordinates, latitude, longitude, elevation, and time steps. These are converted into Earth center, Earth fixed coordinates, X, Y, Z, T. And then just like Grid 4D, we fit them into multiple sub-encoders, EXYZ, ETXY, ETYZ, and ETXZ. Each one handles a different spatial temporal slice. Then the outputs are concatenated and passed through a multi-resolution hash encoder to produce a single 192-dimensional embedding vector. You can kind of think of this process as a fingerprint at any point on Earth at a specific time, capturing both its spatial contents and temporal state. And this allows downstream models to query what the world looked like here and then with one compact vector. So a foundation for large-scale geo AI. And how fine is this encoding, you may wonder, since it's like for the whole Earth. And Earth 4D uses 24 resolution levels for both space and time. And spatially, it ranges from roughly 400 kilometers per cell down to about 5 centimeters, the size of a lime or a small egg. And temporally, it spans from around 11 days per cell down to 0.1 seconds. And together, the default model produces 182-dimensional outputs that requires about 11 gigabytes of GPU memory. And this gives a theoretical sensitivity of about 4 centimeters and 0.1 seconds across the planet between 1900 to 2100 as default to the Earth 4D. And because the hash tables are independent across levels, we can also parallelize training. One GPU can handle a regional or time slice, and the other they cover the globe. So the process won't take too long. And so Earth 4D isn't just a model, it's an architecture that has potential to scale with data and your computing power. And next, let's talk about the hash collision profiler, our latest tool for testing how the encoder behaves internally. So some background information on this is that a hash table is like a big lookup library. Each coordinate is mapped to an index, but sometimes two very different coordinates land in the same spot. That's what we call a hash collision. And when there's too many collisions, which means that the model may confuse distinct regions. And the profiler generates synthetic dataset with 10 different spatial and temporal distributions as listed here. So from uniform global points to tiny 10-meter clusters or repeated hourly samples. So we run them through the encoders to see how collision rates change across levels. And this helps us answer a quick question. How do different spatial temporal data patterns influence the collision behavior in Earth 4D? And I have some quick results to show. And the first one is with the small 10,000 point data set. So you can see here the 4 grids, and the colors show collision rates. The lighter one means low, and the darker one means high collision. So at this scale, collisions are mostly manageable, under 50% for most scenarios. And when you notice the uniform random data, it has the best performance, while dense 10-meter clusters or repeatedly temporal bursts cause more collisions and 5 levels. And these results help us tune table sizes and choose resolutions wisely so that we can use our memory more efficiently without sacrificing precision. And this slide shows another experiment with 1 million points for the input. So when we increase the density to 1 million points, collisions rise sharply, and many 5-level grids reach 80 to 100% collision rates, especially in spatial clusters. And temporal grids tend to climb even more because nearby time steps are similar. So in practice, we found that around 50% of 5-level indices and level 20 and above, 20, 21, 22, 23, declined, which motivated our next step. We are now designing learnable hash probing, making the hash function itself learnable. So the basic idea is to let the model adjust how it maps coordinates into tables and to add a regularization loss that would penalize unused or overly sparse memory regions. So in short, we want the encoder to learn how to use its memory more wisely. So to close up, Earth 4D is part of a broader vision, bringing the history of photorealistic 3D reconstruction into Geo AI, encoding our planet continuously through space and time, efficiently, scalably, and soon would be learnably. And then will be Brandon's part. So Brandon is a PhD student from University of Houston, and he's been doing amazing work and contributes a lot to the work of Earth 4D, and also studied the Alpha Earth and some specific data set that he will be presenting. So I'll have a word to Brandon.
Hi,
And
everyone.
I think Brandon is here. Yeah.
Yeah. Thanks, Shin. Hi, everyone. I just noticed, but despite what the name says, I'm not Lance. I'm actually Brandon. So, yeah, nice to meet you all here. I'll just pull up the slides. Just a sec. Okay. Okay, cool. Oops. Okay, yeah. So, yeah, great to be here. I just want to say, yeah, I mean, since great introduction by Lance. I also agree, like the iGuide thing we, in August was amazing. I think we did a lot of cool things there. So I'm excited to kind of show some more stuff we've been working on. So I'll kind of bring it back to the, I would say now, like this kind of application of like, we're talking about wildfires and stuff. So let me just make sure I don't go over time. Okay, so basically we are looking at sort of predicting this thing called the live fuel moisture content, basically. So, and that's, it's important for wildfires because, can, it help for predicting what areas could be burned or more vulnerable. So, and we do have to do this thing of actually taking the field samples and sort of putting them in the oven and then weighing the mass and all that. So fortunately, this paper did come out that has a sort of global data set. So we're kind of leveraging that. There's a lot of these field surveys that are combined in here. And for us, we are kind of focusing on the US, the continental US, because that's where it's sort of the most dense kind of sampling location. So we kind of just made a training data set out of this where we just try to predict the LMFC value. And we have everything that can be used also for this sort of spatial temporal model. We have latitudes, longitudes, times. We also have like the elevations and stuff. So we also have the name of the species at the area, which we try to use also because that can be pretty useful overall. So, and I'll kind of show what happens when we kind of take into account the species. And what I mostly worked on was using the Alpha Earth foundation model that came out. They sort of, take a lot of data that's on Google Earth Engine, optical data, radar data, LiDAR, some climate elevation, also text data, and they, have the self-supervised model that actually creates 64-dimensional vector representation over the entire Earth's surface at like 10-meter pixels. So we just want to use that and say, okay, this has compressed all of the data from Google Earth Engine into these vectors, and can it help us sort of predict the fuel moisture content, especially in areas that are not sampled, basically, because this data set is pretty sparse because it's from field surveys. So and this is just one example of what the Alpha Earth sort of vectors kind of look like if you try to just visualize them. So we can see that they do represent a difference. This is like, Bay Area of near San Francisco. The sort of urban areas do have a different representation in the sort of embedding space, and the and whereas these more forested areas and coastal areas also kind of have different representations. So the first, I don't think this, I think this is supposed to be an animation, but if I remember, but either way, we just kind of first tested to see if we can go back and forth between the Earth 4D vectors and Alpha Earth vectors. So and overall it worked pretty well. So that's just kind of what this is showing in this area. So basically this, yeah, well, okay, I'm just looking at this, but it's just like showing that basically we can probably have a spatially aware model, but also a model that takes advantage of these actual vectors here. So I'll just kind of go into here and how we used it for the LFMC. So all of these points are actually samples in the LMFC dataset. So like I said, yeah, it's pretty sparse. So what we did is we just take an area and we get the Alpha Earth embeddings, and we have this vector. And since all of this has been sort of, you could say, pre-computed in the Alpha Earth model, we can actually make a very light model that's just a sort of basic neural network, just multi-layer perceptron. And we just ingest it that way and we predict the LMFC value. And incidentally, we have done the same thing with the Earth 4D embeddings. Just take the vector and just pass it into the same network. And so we've done different combinations of Earth 4D and Alpha Earth. And we just take the vectors and just concatenate them and just pass it into this sort of network. So this is what you get if you just only use Earth 4D. But if you use Earth 4D and the Alpha Earth embeddings, you get you sort of get about, I think on average, like 12 or 15% improvement in the error of predicting LMFC. So, and another way to look at it is if we separate this into different components, and we do kind of an ablation. On this top, these like warm colors is if we don't do species embeddings, which I'll talk about, which is basically we make another vector. In this case, say there's 768 species, we make another vector of dimension 768, and we concatenate that too. So, and it just learns and updates these vectors based on the species. So it kind of learns species. So this is sort of without taking any embeddings for species, and these cool colors are with species embeddings. So we can actually see, I mean, all of these are kind of up here, but when we actually include the species, which we have in the kind of original Globe LMFC dataset, then actually we kind of break down into a lot lower sort of loss area, basically. And overall, the improvement from adding this alpha Earth into Earth 4D is down here, but overall, we see the biggest difference right now in adding species. But another way we looked at it is with like making a test data set temporally, like we just cut out some time period. And we also see, I don't show it here, but the alpha Earth embeddings do show the good improvement there also compared to just the Earth 4D model. I also tried adding in some climate data, but right now the improvement is not there yet, but it may be that now we're making a lot of very long vectors, so we may need to kind of increase the complexity of the model also. And another, oops, clicked on it. And so another thing we are trying to add is this sort of bioclip embeddings. So we get, instead of sort of just making a vector and learning this in the model, we may actually kind of get these language-based embeddings for the species that are in the data set. And in this case, it's a clip-based model. So it sort of is doing, what it's doing is bringing text and images into the same sort of space so that you can kind of go between them. So we are still working on that, but it's a work on progress, and we have tried to add this in, but as of now, that hasn't improved the results, or we're just making our own sort of vector for the species and learning that as the model trains. And so that's kind of like the wildfire part. And right now we are just expanding, well, we are working on that, but this can be expanded for other topics, because all of this we talked about today can totally be applied for other things, like this pollination we talked about at the beginning, or this thing of flowering and stuff like that. Yeah, sorry. There's a picture of a flower, but I forgot the word. But yeah, so we want to also do that, because all of these, you can get space-time coordinates, you can get embeddings for all of these. So eventually we can have a series of models for these different topics. So this is kind of the bigger picture of where it's going also. And I think that's it for me.
Thanks, everybody. We appreciate it. Diana, if we can close up the call, and we just want to say thanks, or we can open up for questions. I mean, if that's a normal process here.
No, let's definitely see what questions are out here. That was
Cool.
really interesting.
Thank you. Yeah, thanks.
So it sounds like some of what you were describing was things that happened during those few days together, and then it sounds like other things have been what a few of the team members have been able to continue to test and run in
Yeah.
the couple of months since we were there in August.
That's exactly right. I can characterize that in a nice way and say I'm not really sure if we would have gotten to where we are today without the NSF Guide week. And I say this specifically as in because we sort of had a whole week, and Chin had a whole week to go after Earth 4D, and Brandon had a whole week to focus on Alpha Earth, and so those were really foundational. But that's really just starting to carve it out. The code was very messy. It took a lot of work to. I mean, even as we dug into what we did, we realized, like for Earth 4D, that like there's quite a few. I don't want to say it was wrong. It's just that it wasn't quite right, and so we needed to kind of clean up some things. So we've really turned it into a fully featured engineered system at this point, and that's just for Earth 4D. DeepEarth is still evolving. So yeah, so I think basically, we give credit to NSFI Guide for sparking this, but you guys have also really sparked this collaboration. We're talking every week, every other week, working on it, just producing more results. We're excited for what we mentioned at the NSFI Guide program, which is to pursue like a publication in Nature or Science. I think that would be really exciting. So yeah.
Yeah, that's good to hear about. I mean, the few days together is that we're able to support during the summer school is really meant just as those seed opportunities to begin to work on things and be able to brainstorm some work activities while you are there together. But a lot of these are complicated programs and problems, and obviously they take more than just 96 hours of time to work on. Anand, did you have a question? Otherwise, I'm going to make sure anyone from the audience, feel free at this point to turn on your camera, unmute yourself. You can also still chat or put a question in the chat space. So it was interesting. I remember when Alpha Earth came out during that week in August, and there were it was kind of that opportunistic situation to explore that, see what it was about, how it was going to affect what your plans might have been. So sounds like it was, pretty formative as you would have imagined, but
Yeah.
but
Yeah, it was sort of like we had our plans going into the program, and then I think it was like a week before this like bomb drops. And the story is that, you know, we had been sort of putting stuff out there for Deep Earth for like 8 months prior or something like this. And Alpha Earth really did like I would say like 70% of what I wanted to do with Deep Earth. So I was like, all right, let's just put that on hold and let's go with Alpha Earth. And then, we were able to really focus on things around Alpha Earth that we didn't, that still hadn't been done that we wanted to do. But with the whole plans completely changed. The other thing that was sort of last second that actually resulted in something very interesting is a connection to the Allen Institute for AI. Basically, we saw some results the day before going to Boulder, Colorado, where they actually were taking the same exact LFMC data set. They did the same similar, self-supervised learning of climate and all these different things. And I was like, well, I guess we can't repeat their results either. And so, but it turns out that that led to the collaboration. I remember I was writing them an email from Boulder, Colorado, and saying, hey, I'm here with these PhD students. Do you guys want to collaborate? That ended up leading to an invited talk at the Allen Institute for AI in Seattle. And I flew out there, and it was just this really great moment to bring it all together. So, um, yeah, anyways, just kind of recapping the story here. Um, Chin, I kind of want to ask Chin a question.
yeah,
Chin,
of course.
what was your experience like when you were sort of like trying to, first of all, what did you think of the project? And then, how did you sort of handle what was going on when the CUDA errors were flying, and what was your sort of mentality? I'm kind of curious. This is like a post-game, chat, like a sports interview.
Yeah, I think I wasn't sure that I would be having the CUDA compilation issue happening every day when we, into the HPC. So, well, it's actually an easy fix. So I copy and paste the code that could fix it into a Google Doc. So I run the code. Like it can be wiser, like to do it like a script. But yeah,
I
but
remember we run that like
but
20
we
times.
fix it like eventually, right?
Yeah. So maybe say one more thing, Chin, about Claude Code, because I think we ended up, I'm not sure if we would have succeeded without the latest AI coding tools as well.
Yeah, it is so true that I didn't know Cloud Code would be this powerful and helpful before joining the summer school. And that Lance taught me how to prompt engineer and to kind of get the pipeline to Cloud Code to work while you
Yeah.
have a big picture in your mind for what you should accomplish, for coding or for the project. So I really appreciate the summer school, iGuide and Lens and my other teammates that I had a wonderful week in Colorado. And what more importantly is what I learned from a summer school that also supported me during my PhD journey, like after the summer school ends. So really feel it's a blessing opportunity to be part of it. And actually, my PhD co-worker, like also a PhD student, also in this chat. So yeah, I would encourage him to apply for the summer school next year.
We will have there is one more round under this cycle of funding, there is one more iGuide Summer School. Its
Okay.
dates have been announced. It's July 2026. I don't remember the exact July dates, but it will take place at University of Minnesota, not in Boulder this year.
Okay. So what would be the topic? Is it like
I can't, it's not that it's secret, but hasn't been,
okay,
the
cool.
group hasn't fully decided yet, but it will continue to, inevitably, it will continue to have a focus on GeoAI.
Yeah.
I'm gonna throw out digital twins. Oh my God, I'll give you something. No, it sounds good.
I had one question that just you brought up using Claude, and I remember that was something we went back and forth with at the beginning, Lance, about being able to, that balance between having the summer school build systems, make progress on things
Good
using
question.
only available open tools
Yeah.
versus the
We had an
trade-offs
interesting experience. I can comment on that.
yeah.
Basically, we showed up thinking, the students will remember me explicitly saying, I don't want to break any ethical rules here. It's all on the fair level playing field. I can't just give you this advanced tool. And so we tried using Google's, CLI tool, and it was embarrassing because I'm like asking it to do things and then it wasn't working like Claude. And I was like, you know what, guys? And I pull up Claude and it just starts crushing it.
Yeah.
And then I was like, but I can't, like I can't have you guys do anything. And then I think it was Chin and Brandon and a few others were like, well, they can't stop us from paying for it on our own. And basically, but I think the message really is, to NSF and to administrators that these are tools that everyone should have. And they're not that expensive. They are a real cost, but the power is like having Einsteins and all these different, collaborators with you. And so it does feel like the spirit of Einstein is like with us. And the spirit of, these great engineers are just with us. And that's why Chin and like we appear to be so incredible. In reality, we're humble and we're trying our best, but the AI tools are helping us to do a lot more. So that's the reality. I don't think we would be achieving this work without that, basically.
Well,
Oh,
yeah, I have something to say at this
Yeah.
point. So, like, I introduced the call code to my coworkers and my supervisors, and ended up that every one of us have him, like, our supervisor, to pay for our call code. And it's like no Pro Max, but like he thinks that's fantastic to boost our efficiency and productivity with cloud code.
Good.
Yeah.
Yeah.
Very cool.
Well, I'm glad that it all worked out just for what the project needed then.
Yeah,
All
no, we
right.
did it.
Thanks again, everyone. Any final opportunity for question from the audience? If not, you can always, I'm sure that our presenters would be happy to follow up separately if you drop them a line, send them an email. The recording for this will be processed and put up on the iGuide website. We've got another series of topics coming up over the next few few weeks steadily through the end of the calendar year and then all the way into January, we're starting to schedule these VCOs. So thanks everyone for coming today, and we look forward to following up. Lance dropped his email in the chat there if you want to follow up with him. Lance at ecodash.ai, and you can find our other folks at their university web pages too. So
Inviting collaboration and any questions for any of the folks, I'll connect everyone together. So thanks, Diana. Thank you very much. And thanks to NSF iGuide. Thanks, Anand. And thanks to Xiaowen, who's here with us in spirit. Anyways, we're really appreciative. So thanks so much. It's been an absolute
All right.
pleasure.
Kudos, team 3, live fuel moisture content team.
You've heard.
All right, take care. Bye, everyone.